Welcome students. So we will continue our discussions on OFDM. So in the last lecture we saw that how you can have a multi-carrier system and then how you can have the frequencies, the subcarrier frequencies spaced apart by a multiple of 1 over t, where t is the symbol duration, so that you can have overlapping but orthogonal subcarriers. And then we saw how to implement a OFDM system using IDFT, and how cyclic prefix is added to an OFDM symbol, and how, because of the cyclic prefix, your channel ISI effect is mitigated. So today we will also look into the OFDM's ability to compensate the channel impairments. Okay, so let's assume now a discrete time model for the channel. Okay, so let's say the channel has an impulse response, okay, that is defined by these different taps. Okay, so the channel, okay, let's say this is the discrete time model of the channel, which is defined by Hn. Okay, so Hn is basically the different samples of the channel impulse response. Okay, so they will have different amplitudes and they have different delays. Okay, so they will have, let's say, tau 1, let's say this is tau 2, and so on. Okay, so these delays, let's say the channel has m such taps, okay, small m. Okay, so if that is the case, then the received nth sample is the channel impulse response convolved with the input fn minus j plus wn, and here your j is between 0 to m, where m is the number of taps in your channel. Okay, so basically this part is the discrete convolution, right? This is the discrete convolution of your channel with the input. So if your OFDM, so these are your inputs. Okay, and then here you have the channel, and then here you are adding noise, and whatever is, this is the received thing. Okay, received discrete time signal. Okay, so the sequence Wn, these are the AWGN noise, complex AWGN noise samples with variance n0 by 2 per real dimension. Okay, and taking n samples, where this capital N is the total number of subcarriers, so these inputs will have total n samples, capital N samples. Okay, so your f is a vector, that's the input vector, which has capital N samples, f0, f1 to fn minus 1. Okay, so now we create the cyclic prefix, so that is, we prepend the final L, capital L samples of f to the beginning. Okay, so we have f0 to fn minus 1, and the final L, which we denote as f minus L to f minus 1 at the beginning, and this capital L should be greater than or equal to the channel delay. If the channel's impulse has m samples, let's say between 0, 1, 2 up to m, so let's say these are the channel whatever, so this has to be at least greater than or equal to m. So we discussed this in the last lecture, the cyclic prefix length. If you go back few slides, so here the cyclic prefix length has to be, equal, at least equal to the maximum delay that you are having. Okay, if it is more than that, then it is even better. So that's what is mentioned here. Okay, the cyclic prefix length capital L has to be greater than or equal to the channel impulse response length. Okay, so here we have, since we are prepending the final L samples to the beginning, so for j equal to 1 to capital L, we have f minus j equal to f of capital N minus j. So basically f minus 1 is basically f capital N minus 1. Okay, because we are prepending the final n here, and f minus L is capital f n minus capital L. Okay, so let's say that's what is happening. Okay, because we are prepending the final L samples at the beginning. Okay, and for j equal to 1 to m also, since L is greater than or equal to m, for j equal to 1 to m we have the same relationship. Okay, so so with this, if we write that discrete time received sample expression, then this will be written, if you just write them and expand them. So r0 will be this, r1 will be this, and so on. And then if you use this cyclic prefix, this relation, then these equations can be written in a matrix form like this. So where you have this received sample vector r0 to r capital N minus 1, and then these are the channel coefficients, and then you have the input vector f0 to f capital N minus 1 plus the noise. Okay, so in other words, you can write r equal to hf plus w. Okay, and because of this this cyclic property of the input samples, okay, this cyclic property of the input samples for j equal to 1 to small m, where m is the total number of taps in your channel impulse response, you can write this matrix, okay, as a circulant matrix. So H, capital H, okay, this capital H, this matrix is a circulant matrix. Okay, so basically the circulant matrix is such that you have, basically this will be a circular convolution. Okay, whatever you are doing between this matrix and this matrix multiplication, this will behave as a circular convolution. Okay, and this matrix, this capital H, is a circulant matrix. Okay, so if H is a circular matrix, because of this cyclic prefix addition and the properties of these inputs, you can verify that this H, so these all these equations, if you replace this f minus 1, let's say, with let's say f minus 1 is f of capital N minus 1. Okay, so f minus 2 is capital F n minus 2, and so on up to this m. Okay, where this j runs from 1 to small m. If we replace this minus indices with capital N minus whatever, so then, and then if you arrange these terms together, then this matrix R, this R0 equal to, sorry, this R vector equal to this matrix times the F vector plus the noise vector, then this matrix will turn out to be a circulant matrix. Okay, so if we invoke the result that any circulant matrix may be diagonalized by this, okay, so where U is the DFT matrix and U Hermitian is the IDFT matrix. Okay, so this again, this is not new. I am assuming that you have come across these concepts in your DSP class. Okay, if not, then I can explain it further in a live session. But right now I'm assuming that you know this part. So H is a circulant matrix, and you can invoke this transformation on a transcirculant matrix where U is the DFT matrix and U Hermitian is the IDFT matrix. Okay, so this means that multiplication of a vector by U is the same as taking the DFT of that, and U Hermitian, or the Hermitian transpose of U, is the conjugate of the transpose of U. Okay, so, and this H bar is the matrix which is the diagonal matrix. Okay, so where all these diagonal H0 bar, H1 bar, H2 bar, etc., this is the DFT of the first column of the original matrix H. Okay, so with this arrangement, okay, U Hermitian equal to H bar, you can write your actual matrix H as this. Okay, so basically you take U Hermitian this side and U this side, so you get this. So if you do this from both sides, you will get H equal to U Hermitian times H bar times U. Okay, so your received signal is basically HF plus W. So H is this, so basically this times F plus W. Okay, and let's say if you let R bar as U times R, F bar as U times F, and W bar as U times W, then you might write capital R bar equal to capital H bar plus capital F bar plus W bar, capital W bar actually. So then you can see that this H bar is a matrix which is basically, sorry, this H bar is a matrix which is a diagonal matrix. Okay, so which contains across the diagonals all the elements which is the IDFT of the first column of H. Okay, so you can write that, you know, Rm bar is basically Hm bar, and this F bar is the Fm bar. So these Fm bars basically are those elements. Okay, so you are generating your F, okay, the samples of your OFDM from Fm bar. So basically all these Fm bar these basically these FNs were obtained by the endpoint IDFT of all these FM bars. Okay, so these were the endpoint IDFT of all these complex FM bars. So now this is basically the DFT. This F, capital F bar, is basically the DFT of the input vector F. Okay, so basically F bar is the DFT matrix times the input vector F, So essentially you are getting back all those FM bars here. Okay. So basically this RM bar is HM bar plus FM bar plus WM bar. So these are basically nothing but the same FM bars from where you actually obtained the OFDM signal. Okay. So therefore you can see that there are n parallel sub-channels in the frequency domain. Some sub-channels have better SNR than others. Okay, so depending on these HM bars, okay, some HM bars are higher in strength, some are low. So some sub-channels have better SNR than others. So these may support higher order constellation. Okay, so those which have higher SNR, this may support higher order constellation. So again, let us go back a few slides back when we were generating the OFDM here. So we were generating this capital F, M, capital FMs. So these are F0 to F capital N minus 1. We were generating these through some QAM modulators, and I said before that these QAM modulators shouldn't be the same QAM. So based on whichever HM is higher, so this M and this M, so this M runs from 0 to N minus 1. Okay, so for whichever your HM bar is higher, that particular channel can, you know, handle a higher order QAM. So this M0 QAM can be 64 QAM if your HM bar is higher, and this M1 QAM can be 16 QAM if your H1 bar is lower. So that's what we are deriving here. So whichever channel, so this is an equivalent parallel channel model of the OFDM where each of the M's are corresponding to a separate subcarrier. So we have different parallel channels for different subcarriers, okay, up to N minus 1, and each of them is basically, you know, you have this HM, also this is H0, this is H1. Okay, so this is, let's say this is F0 bar, this is F1 bar, and so on up to F N minus 1 bar, and then you are basically multiplying these with your H bars, and then you are adding noise, okay, for each of these parallel channels. Okay, so the noise is getting added. So this is W0 bar, this is W1 bar, and so on, and then you have the received. Okay, so this is R0 bar, this is R1 bar up to Rn minus 1 bar, and so whichever sub channel has a higher HM bar, that have a better SNR, and that can support a higher order constellation, and this concept is called bit loading. Okay, so also note that the sequence WM bar consists of the AWGN with the same statistics as WN. Okay, so we basically transform the OFDM symbols or samples into a equivalent parallel channel by doing all these transformations, and then we are deducing that what will be the mapping, or what modulation we'll be using on each of these OFDM symbols from which so each of these complex symbols from which the final OFDM samples were generated. Okay, and each of them can have a different modulation based on how much SNR each channel can support. Okay, and in this way we can compensate the channel impairments a little more. Okay, so moving on with OFDM, so there are certain difficulties of OFDM also, and the first thing is that OFDM, because it is a sum of different subcarriers, it has a very high peak to average power ratio, which is called PAPR. Okay, and usually in real systems, when you are using power amplifiers to amplify the signals, all the amplitudes need to be amplified equally. Okay? So usually the amplifiers have this input-output relationship where K is the amplification factor. So the amplifier should have a linear characteristics with slope K on a V out versus V in curve. Okay. But practical amplifiers have limited linear ranges. So what I mean is this. Okay. So the limited linear range is this. Okay. If we increase the input power further, then it's not ideal anymore. It just saturates. So practical amplifiers saturate beyond a certain range. Okay. So if your combined OFDM signal has an input power more than the linear range of a practical amplifier, because you are adding so many signals, because you are adding many signals, there is a chance that the input voltage, the total input voltage, goes beyond the linear regime of a practical amplifier, and it goes to the nonlinear region. Okay, and therefore there is a problem, and the problem is that if your signal is too high in amplitude, then it will clip the top of the signals, and because of that there will be a lot of distortion in the signal. Okay, so why PAPR is an issue in OFDM? So let's say your PAPR is defined as 10 log 10 of the maximum value of the signal multiplied with its complex conjugate, and then the average value divided by the average value of the same. Okay, so let's, for a single carrier system, let's imagine that your XT is of this order. So let's imagine the amplitude is 1. So in that case your maximum value will be 1 because these two cancels out, and the average value will also be 1. Okay, so the PAPR is 0 dB. Okay, but for a OFDM signal where you have the sum of different complex signals, so if you do FT times FT conjugate, then the maximum value will have approximately n squared terms, where n is the number of subcarriers. Okay, and the average value will have n terms. Okay, so that's why the average value will have n terms and why the maximum value will have n squared terms, I am leaving you as an exercise for you. Okay, this is an exercise. Okay, you have to prove it yourself. Okay, and you can hand this to me. Okay, and I will have a look. Okay, so so if it has n squared terms and if it has n terms, then the PAPR will be of the order of 10 log 10 n. So the PAPR actually scales up with n. So if you have very high number of subcarriers, let's say n equal to 1024, which is sometimes the case, or 2048, then this PAPR is very high. Okay, so that is a problem, and basically this is a mathematical expression, but in general, if you have so many subcarriers added, then there is a chance that you will face this problem when you are passing through an amplifier. It will go beyond the linear range of the amplifier, and there will be signal distortions because of that. and that can be captured well through this PAPR expression. And this PAPR is scaling up with n, which is very intuitive and obvious. Okay. So expensive amplifiers have wide linear range. Okay, so you can use expensive amplifiers, or you could reduce the peak amplitude. Okay, so this is called input back off. Okay, but this would decrease the signal to interference plus noise ratio, and then that will be another problem to solve. So specific PAPR reduction techniques can be used. So specialized coding, phase adjustments, clipping, etc. can be done, or you can use single carrier FDMA. So this is a technique that is used in 4G. There are other difficulties of OFDM. So you can have carrier interference. Okay, you can have different reasons for these intercarrier interference. Sometimes cyclic prefix can help to reduce the intercarrier interference, but not always. So this is another problem with OFDM. So talking about OFDM, we should also talk about OFDMA. So this is orthogonal frequency division multiple access. So this uses OFDM to share the wireless channel. So when many users are using the wireless channel, each of them can use one subcarrier to transmit, and then one or more subcarriers out of available number of subcarriers. So different groups of subcarriers can be used by different users, and the subcarriers are allocated in groups called subchannels or resource blocks. And usually it's too much computation to allocate every subcarrier separately, and that's why they are allocated in groups. And when you are allocating these subchannels, okay, there should be some rules. So if you are allocating adjacent subcarriers, then you might end up having similar signal to interference and noise ratio between two users. So you can have regularly spaced subcarriers to diversify the SINR. You can also have randomly spaced subcarriers, so this will diversify the SINR, and also it will reduce the adjacent cell interference. Okay, so this is how you can allocate different subchannels, and each subchannel can be identified with a pilot subcarrier. So this can be used by user 1, this can be used by user 2, etc. to uh, access the wireless channel. So so you can also have opportunistic scheduling. So to schedule the subcarriers or the subchannels and the power levels based on channel conditions and data requirements. So you can adjust in a dynamic fashion. So how to use channel variation as an opportunity to schedule the best choice in users. Okay, so if the channel is having a frequency selective fading at a certain frequency range, then you can avoid the subcarriers within those frequency range, and have some set of subcarriers where the channel frequency response is high. So that is what is called opportunistic scheduling. So there are different criteria of opportunistic scheduling here, so you can have a look. And then talking about single carrier FDMA, so this has a similar structure and performance to FDMA, but it has lower PAPR. So when you are using your mobile phones, okay, so if you are having single carrier FDMA, so the PAPR is low, and that actually benefits in terms of battery life, power efficiency, and also the cost. And this is good for uplink. So uplinks means from your mobile phone to the base station. Okay, So your mobile phone will use SC-FDMA. While downlink from base station to your mobile phone, the base station can still use OFDM, because in the base station there is not much limitation in terms of this PAPR and battery life. But for your mobile phone, this has to be, long battery duration, and the phone has to be power efficient. If you want to have OFDM in your phone, then the phone cost will be high also. So to generate SC-FDMA, you use extra DFT operation and frequency equalization compared to OFDM. So basically you have a DFT prior to the IFFT that spreads the data symbols over all subcarriers, and every data symbol is carried by every subcarrier. Okay. So we will I'll show you a video. Okay. So this is the OFDM. This is the OFDMA, where we have multiple subcarriers, and this is the single carrier FDMA. So we will discuss this more when we will study 4G LTE in my wireless communication module. Those of you who are in my wireless communication will revise this concept. Okay. So let's watch this video. Okay. So to get your concepts clearer about this SC-FDM and single carrier. So I will stop here and show you the video.
Streams of data in the form of bits reaches network gateway from various sources. The gateway forwards it to the E node B, but how does the E node B converts them into radio signals and transmit them to the user over the air interface? How does the user equipment communicate back with the node B? Hello friends. Welcome back to the world of 4G. Today we will discuss uplink and downlink data transmission in the network.
As discussed earlier, data is transmitted in OFDMA over parallel subcarriers of 15 kHz. The subcarriers are further divided on the time axis as blocks of one symbol duration, or 66.7 microseconds. This basic unit is known as resource element. Each resource element carries one symbol. Now, in order to transmit data over these resource elements, first data is modulated with specific modulation scheme. This scheme depends on the physical channels mapped on the resource grid. Suppose we have 8 bits of data to be transmitted using QPSK modulation. The data will be divided into 4 parallel streams of 2 bits. Phase and amplitude assignment is done according to the QPSK constellation. Finally, data is placed over the resource elements by adjusting the phase and amplitude of subcarrier to those derived for the data stream. Mathematically, it means multiplying the complex modulation symbol to the corresponding subcarrier frequency. Thus, in a 20 MHz channel, all the 1200 resource elements carrying 1200 symbols over 1200 subcarriers are modulated with appropriate modulation scheme. Now, since the data is modulated over 1200 subcarriers, a transmitter will require 1200 oscillators for its generation, and another 1200 will be required by the receiver for proper demodulation. The hardware complexity and sheer amount of power consumption would have left OFDM to theoretical idea and far from implementation. OFDM was made reality with the advent of digital signal processing techniques. So, instead of using 1200 oscillators, IFFT solves this problem by converting the parallel frequency domain signals into samples of a composite time domain signal, which are much easier to generate at transmitter side. All we need to do is to send these time domain samples at radio frequencies. As the data is being sampled by IFFT, samples must be taken above the Nyquist rate for faithful reproduction at the receiver. For an LTE spectrum of 20 MHz, the highest frequency component is 9 MHz, which means the sampling rate should be greater than 18 megasamples per second. In other words, 1200 samples per OFDM symbol of 66.7 microseconds. Since UMTS had a sampling rate of 3.84 megasamples per second. To achieve backwards compatibility, Sampling rate in LTE is taken as multiple of 3.84 megasamples per second. Thus for 20 MHz spectrum which has a sampling rate of 30.72 megasamples per second, there are 2048 samples per symbol in OFDMA. The FFT size of the IFFT processor thus depends on the LTE bandwidth as shown.
Now, previously we have shown, in wireless channel due to multipath propagation, we face delay spread and inter-symbol interference. We have also discussed how its effect can be reduced by increasing the symbol duration. Also, how guard period were used to eliminate it. But abrupt changes in time domain during transition period, from symbol to guard period causes intercarrier interference in frequency domain, and disturbs the orthogonality between subcarriers. So in OFDMA, we employ a more complex kind of guard period, called cyclic prefix, in which end part of a symbol is transmitted in the preceding guard period. It also ensures orthogonality between the subcarriers, by keeping the OFDM symbol periodic over the extended symbol duration and therefore, avoiding intercarrier and interchannel interference simultaneously. Since OFDMA uses composite IFFT samples, cyclic prefix is added by taking some samples from the end of a symbol period, and placing them at the beginning.
Now this time-sampled signal is converted into analog wave by a digital to analog converter. Further composite waveform is modulated at the desired radio frequency for transmission. For an example, an operator having license for 2320 MHz to 2340 MHz. The 18 MHz band will be mapped from 2321 MHz to 2339 MHz using analog modulation. And finally the A node B transmits signal over air. In node B, informs the user about the allocated subcarriers and the corresponding modulation scheme. So, when the RF signal reaches at the user's terminal, all these processes are reversed and finally user is able to receive the data intended for it.
Although there are many positives in OFDMA, but IFFT summation of multiple parallel subcarrier results in high peak to average power ratio. High PAPR results in high power consumption for signal generation, but handheld devices have limited power capacity. This makes OFDMA unfavorable for uplink transmission. In order to overcome this, LTE uses SC-FDMA in uplink direction. In OFDMA, we have one-to-one mapping between symbol and subcarrier, but SC-FDMA allows a symbol to be transmitted in parts over multiple subcarriers. For example, in OFDMA one symbol occupies one subcarrier of 15 kHz, but in SC-FDMA, same symbol is distributed among multiple subcarriers of 15 kHz. In short, SC-FDMA behaves like a single carrier system with short symbol duration compared to OFDMA. To achieve this, SC-FDMA introduces the endpoint FFT block right after the serial to parallel converter in the OFDMA structure. The FFT block converts parallel sequence of symbols in time domain to different frequency points. Now, peak to average power ratio is proportional to the square of number of carriers involved. SC-FDMA reduces PAPR by reducing the number of carriers. Obviously, there are problems in single carrier transmission as we discussed earlier, but the side effects are reduced by ensuring that the total bandwidth over which a symbol is transmitted is still not too high. Apart from this, remaining block in the uplink direction is same as used in downlink direction.
In our next video, we will be talking about physical, transport and logical channels used in long-term evolution. So friends, don't forget to subscribe to our channel, like our videos and comments, reviews or suggestions.
So welcome back after that video. I have very little part left in this video lecture. So basically I have some OFDM practice problems for you. So problem 1, so let us look back on the IFFT expression for an OFDM symbol, which is given by this expression. So the received signal can then be written as a discrete time convolution of the symbols fns and the channel impulse function as this. So assume that you have a 16-point IFFT. Okay, let's take some simple examples to get your concepts clear. So let's say you have a 16-point IFFT, so therefore your capital N is 16 and a cyclic prefix length of L equal to 4. So write down the expression for the cyclic prefix added OFDM sequence F and write down the expression of all the received OFDM symbols. Write down the channel matrix H from part B and show that it is a circulant matrix. So you have F which is like this. So this is the general expression. So here your N is 16, so you will have N minus 1 F0 to F15. Okay, and this will be the L is 4, so F minus 4, F minus 3, F minus 2, F minus 1, and basically F minus 4 is equal to F15. Okay, because the last 4 is copied in the front. Okay, so F minus 3 will be F14. Okay, or it's the other way. So your F minus J will be F N minus J. So F minus 4 will be F11. So this will be F11, sorry. This will be F11, this will be F12, this will be F14, and this will be F15. Okay, so this will go here, this will go here, and so on. Okay, so then if you write the channel, I mean the received samples, then this will be like this. So if you use this fact that for L greater than equal to M we have this property, then you can write down the final expression. Okay, I don't have the solution for part C and D for some reason, or do I have it? Let me see. Sorry. Okay, for some reason I don't have the solution. I will give it to you later for part C. Okay, but you can work it out yourself. Okay, with this property. Okay, so let's look into the next example. So consider a delay spread of approximately 3 microseconds. So what is the minimum number of subcarriers necessary in an OFDM system over a bandwidth of 10 megahertz to overcome ISI? So for each subcarrier to experience flat fading, we need OFDM symbol time T greater than this this 3 microsecond. Okay, so that will give your N over B. So OFDM symbol time is as B is the bandwidth, 1 over B is the actual symbol time, and OFDM symbol time is multiplied n times by a factor of n, as you learned before. So this N over B should be greater than 3 microsecond, which implies that N should be greater than B times 3 microseconds. So this will be 10 megahertz times 3 microseconds, so 30. So therefore the minimum number of subcarriers required is 30. So if you want to have this as a power of 2, then you can use 32. Okay, which is 2 to the power 5, because you have to do n point capital N point IDFT, and in your IDFT it's better to have a power of 2 for N. So let's move on with the next example. So consider the symbols capital F0, capital F1, capital F2 and capital F3. So these are your the complex symbols. Find the generated OFDM samples without the cyclic prefix. So this is just the, as you have 4 symbols, so basically this will have a 4-point IDFT. So just you do the 4-point IDFT with this these values of FM bar that are given here. So if you do this, you will find that the OFDM samples are of this 1, 0, minus 1 and J are 0.25J, 0.75, minus 0.25J and 0.25. So these will be your OFDM samples. Okay. Next, consider an OFDM system with bandwidth 10 MHz and number of subcarriers 1024. Let the cyclic prefix comprise 1/8 of the number of samples from the tail of the OFDM symbol prefixed in the front. What is the total time of the resulting OFDM symbol with cyclic prefix? So you have the OFDM system with bandwidth 10 MHz and the number of subcarriers is 1024. So the total time of the resulting OFDM with cyclic prefix can be calculated as follows. So the raw OFDM symbol time without the cyclic prefix is basically N over B. Okay, so that is this N is 1024 and this is the bandwidth. Okay, now cyclic prefix comprises 1/8 samples in OFDM symbol, so the total time is 1 plus 1/8 of this this symbol time. So that will give you 115.2 microseconds. And finally we have this example. So consider an OFDM system with the decibel noise power as 10 dB and 1024 subcarriers. Now what is the noise power in dB at the output of the FFT in the OFDM system? So given an OFDM system with decibel noise power of this, the actual sigma square is 10, so number of subcarriers is 1024. So the noise power in dB at the output of the FFT in the OFDM system will be n times sigma square. So each channel, each subcarriers is having this noise power. So there are total n channels. So you will have this. Now the noise power at the output in dB is therefore 40 dB. And then the final example, consider an OFDM system with dB noise power of this. Number of channel taps is 12. Okay, so this is this talks about your impulse response of the channel. Okay, like this. So this talks about this. So this number is 12. Okay, and the number of subcarriers is 256. What is the dB transmit power required to achieve a BER of 10 minus 6 in the OFDM system? So here the BER in the OFDM system as a function of transmit power transmit SNR, number of subcarriers N and the number of channel taps L is given as this. So this is the formula that gives you the BER in OFDM system. Okay, so given this and this can be approximated as this. Okay, so if you are assuming high SNR, so then given the dB noise power sigma square is 6 dB, so this is 4 in terms of normal ratio, and the number of channel taps is 12, subcarriers is 256. So you have everything given. So the BER is 10 minus 6 and then you fit everything here. That will give your P as this. Okay, so this is power in dB will be 76 dB. Okay, So with that I will end this video lecture, and I'll see you in the next one. Thank you.